Okay, so last time we started by talking about statements, right? So do we remember what statements are? They're kind of assertions, basically sentences which are either true or false, right? So here's one thing I want to clarify about statements though. So a statement is something which has an unambiguous truth value, but that doesn't mean that we have to know the truth value in order for it to be a statement. So first, so we may not know the truth value of a statement, but it is still a statement. Okay? So when I say like this unambiguous thing, like a statement having an unambiguous truth value doesn't mean we have to know what it is. It just means it can't like depend on a variable or anything like that. So let me give you an example. So very famous conjecture meaning unsolved problem in mathematics is the twin prime conjecture. So it says that there exist infinitely many prime numbers, so I'll just say primes, p, such that p plus 2 is also prime. So for example, 3 and 5 have that property p. 3 is prime, 3 plus 2 is prime, 5, 7, and so on. So like I said, this is an unsolved problem. Nobody knows if this is true or false. We think it's probably true, but nobody can prove it. This is a statement. Even though we don't know the answer to whether it's true or false, it's still a statement because, either it's going to be true or it's going to be false. There's either going to be infinitely many or finitely many. So in case you're somebody who didn't realize that math is not like all understood, we don't know, there's a lot of questions we don't know the answer to. Okay, any questions about that? That's just a kind of side comment. So at the end last time, we got to talking about tautologies and contradictions. Does anyone remember what a tautology is? Yeah, exactly, yeah. Basically, it's some sort of, maybe like a compound statement, which just by looking at the format of it, it's just always going to be true. So just quickly, tautology, just to remind you, a statement which is always true. And our kind of easiest example was P or not P. Contradiction is the opposite. It's always false. And our kind of standard example was P and not P. Yeah, let me give you another example, a kind of more complicated example than these ones, and kind of let's show that it's determine whether it's a tautology or not. Let's do P. Sorry. P if and only if Q or P if and only if not Q. Okay. Maybe the question is to determine, is this a tautology, is it a contradiction, or is it neither? Okay. So does anyone have a suggestion for where I should start? What method I should apply here? Yeah? Yeah. Yeah, still I haven't given you any other methods to do anything, so we better do a truth table. Yeah, that's a good idea. So we start with our kind of basic variables P and Q, or sorry, not variables, statements. So these are our kind of basic statements, P and Q. Okay. And when you're doing this, what I would suggest, like, to do this systematically, take your expression. Okay, obviously start with the simplest things, P and Q, and then build up to the kind of next most complicated thing, or sorry, next least complicated. So in this case, we've got a not Q. So that's pretty, so that's pretty kind of simple. Let's do the not Q next. And then if we build outward, the next thing, I mean, it's either, we could do P if and only if Q, or P if only if not Q. It doesn't really matter. Let's do this one. That's our next most basic thing. And P if and only if not Q. And then as a last column, we've got the whole thing. So P if and only if Q, or P if and only if not Q. So I wrote some really quick notes. You might find those in the Brightspace. You should find them in the Brightspace for this section under course notes, just about how to systematically write the truth value combinations of two basic statements or any number of statements. In this case, it's pretty simple. So they're either both false, or P is false, Q is true. Q could be true, or sorry, P could be true and Q could be false, or they could both be true. Okay. And then remember from last time how we do this? We start by just writing these down, and then we kind of propagate things into the later columns. So looking at not Q just has the opposite truth value as Q. So we can just write, every time we see a 0, we can write a 1. Every time we see a 1, we can write a 0. Okay. Okay, now this column, does anyone remember how to do this? Yeah?
0.
Exactly, yeah. So remember this if and only if thing checks. This is true if they have the same, this checks if they have the same truth value, right? So if they have the same truth value, it's a 1. If not, it's a 0. So first row, oh, sorry. I'm looking at the wrong columns. Right, we're looking at P and Q. We want to say, do they have the same truth value? They do, so we get a 1. Here they don't, because P is false, Q is true. We got 0, 0, 1, because here they have the same truth value. Now we do a very similar thing, right? But now we compare P and not Q. So it goes 0. These are both false, same truth value, so I get a 1. Same truth value, get a 1, 0. And now we see we want to compute this. We compare these two columns. We do the OR operation. So if one of them is a 1, at least one of them is a 1, we get a 1. We can see there's actually exactly one 1 in every row. So we get 1, 1, 1, 1. And we can say that it's a tautology. Yep. Yeah, my bad. Yeah, sorry. I wrote it correctly there, but yeah, totally. Thanks. Yeah. Okay. I mean, this one is actually, if you think about what if and only if means, it's kind of like we went through all of this work, but it's kind of obvious because either P and Q have the same truth value, right? If they don't, then P and not Q would have the same truth value. So one of these things, actually exactly one of them, is always true. But if you're asked to do a truth table, you should do the truth table, right? Okay, so what I want to tell you about now is, well, a couple of closely related things. So first, we'll talk about logical equivalence. So let's say we have two compound statements. S1 and S2. So we say that they are logically equivalent if S1, if and only if S2 is a tautology. So you should think of both of these things, like S1 and S2, both being like some sort of statements that have like P's and Q's and R's in them, right? And this is kind of, so this is a definition about, when are they logically equivalent. So when they are logically equivalent, so we write this as S1 with this kind of double arrow, S2. So to mean S1 is logically equivalent. So you got to keep this straight. What do the fat arrows mean, and what do the thin arrows, double arrows, right? So this is kind of a thick double arrow, and it means logically equivalent. So let's, this might sound weird, but let me just say, the way you should really think of this logical equivalence is like equals. That basically, S1 and S2 might be two different compound statements that look different, but if they're logically equivalent, then they really mean the same thing. So that's kind of the, whenever you see, if you're trying to prove two things are logically equivalent, you're trying to show that they're actually the same statement, even if they look different. So let's give an example. Here's an example. This is something we actually kind of discussed last time, but I didn't give you any kind of proof. I think I just made a quick comment last time that the double arrow is kind of like two single arrows. Let's prove that they're actually logically equivalent. So position that P if and only if Q is logically equivalent to P implies Q and Q implies P. Okay. So as usual right now, all I have is truth tables. So I'm going to do this with a truth table. So just kind of briefly, I've got P and Q. I can do, let's do P implies Q. So I'm going to kind of deal with these things first. Q implies P. Let's do P implies Q and Q implies P. And let's do, lastly, let's do P if and only if Q. Okay, so if we go back to the definition, so I want to show that S1, I want to show that, this thing, P if and only if Q, if and only if this stuff is a tautology. So it seems like I probably want another column, which is this thing, if and only if this stuff. But because, we're a little bit lazy, we don't really need to make that last column. All we're going to want to do is check at the end if the last two columns are exactly the same. If the last two columns are exactly the same, then this, if and only if that, will be a tautology. Okay, so really what we're trying to do is show that this is the same as that, meaning all the truth values here are the same. Okay, so we do the usual thing. This I can do pretty quickly. Remember, P implies Q is always true if P is false. So I can just go 1, 1. This is the only case where it's false because P is true and Q is false. So P doesn't imply Q. And here we've got true. The other way around, so this is going to be our only false. 1, 1, 1. This is the only time Q implies P is false, when Q is true and P is false. Now we do the AND, so these are both true, those aren't, but those are. So, right. So I'm just applying the AND to these two columns. And now I do my P if and only if Q, which is true if and only if these are the same. Oh, sorry, P and Q. If P and Q are the same truth value. So 0, 0, 1, 1, but these ones are supposed to be zeros. And now if you look at these columns, you see they're exactly the same. So therefore, these two statements are logically equivalent. Because if I made another column, which is this if and only if that, it would be just all ones. You don't have to write the last column. It's enough to just check these are all the same. Is that clear? Is that too quick? Oh, yeah, the last step. So yeah, so what you want to do, the last thing to do, so we end up with our kind of two things on either side of this. So to know that they're logically equivalent, what you need to check is that for every row, the values match. So whenever this one's true, this one's also true. Whenever this one's false, that one's also false, and vice versa. So that they literally match up. And then with that, if they have all the same values on all the same rows, that means that this one, if and only if that one, is a tautology. And yeah, you don't have to write another column for that. It's just enough to say these all match, therefore logically equivalent. Any other questions? Okay. So basically at this point, like the main skill is just be really good at truth tables and know what the question is asking for if it says logical equivalence or anything like that. Okay. Now let me give you a definition which is basically the same thing. So I will try to I'll just erase some keywords here and change them. So, but if you're writing notes, then I'll give you some time. But oh, okay. Actually, this sentence doesn't work anymore. I'll write it again. So let S1 and S2 be compound statements. So say that S1 logically implies S2 if S1 implies S2 is a tautology. And we write S1 with a fat arrow to S2. And again, if you're really good at truth tables, then you can always check if something logically implies the other, right? Let's do a pretty basic example. So, proposition, or actually maybe do I have a more complicated example? Let's see. Okay, let's do this. So A logically implies A or B. Okay. This is pretty kind of obvious, right? If A is true, then obviously A or B is true. But let's make a quick truth table. A or B. The first case, 0, 0, it's 0. 0, 1, it's 1, 1, 1. This time, maybe because, so logical equivalence, like at the end, all we have to check is that all the values are the same. That's a little easier. Let's, in this case, to make sure we're understanding, let's write another column. Maybe you don't necessarily have to, but let's write another column. And let's check it's a tautology. So the first row, I get true because A is false. I again get true because A is false. That's easy. Here we have A is true. A or B is true, so that's true. And here we have A is true, A or B is true, so that's true. So it's a tautology. And therefore, A logically implies A or B. So it's one thing to watch me do these over and over, but like, I really do suggest getting some practice with this. I mean, you'll have a lot of practice on your assignments and stuff like that, but I think, yeah, there's lots of old final exams and stuff. During this term, at some point, get some practice doing these truth tables and kind of recalling these definitions. Okay. Any questions about any of this? Here's something that's kind of apparent. So we kind of just, with the kind of thin arrows, we just showed that if P implies Q and Q implies P, that's the same as P if and only if Q. It's the same thing with this logical equivalence and logical implication, right? So S1 logically implies S2, and S2 logically implies S1. It's the same as S1 being logically equivalent to S2. And actually, you can derive that right from the definition, right? If S1 implies S2 as a tautology, and if S2 implies S1 as a tautology, then S1 implies S2 and S2 implies S1 as a tautology, because if you take true and true, they're true. S1 implies S2 and S2 implies S1 is the same as S1 implies, or if and only if S2. We should just show that that's that those are equivalent, and so yeah. Anyway, I wouldn't suggest ever like using this fact, but this is just an important thing to know. I mean, a useful thing to know, perhaps. Let me just give you another example of this logical implication. Actually, like before I do this with a truth table, like, can anyone tell me? I mean, why should this kind of thing be true? Yeah, like this is just really kind of in disguise. This is just kind of saying this fact I keep on repeating over and over, that if the first part of an implication, or yeah, of a A implies B, if the first part is false, then the whole thing is true. Like that's kind of what this is saying. It's kind of like encoding the fact that if A is false, then A implies B is true. I mean, yeah, but that your description is perfectly good. Yeah. But let's kind of formally say how this, formally kind of verify this with the truth table again. So we got A, B. Let's go with not A, and let's do let's do A implies B. And then I'll make a column for not A implies A implies B. I think if you don't want to write this last column and you just, at the end, you just argue that, everything worked fine, that'll be enough. But to be safe, let's write this last column and just show it's a tautology. And note how I put the brackets, right? Please, please, please remember to put brackets in these things. Okay. So, as usual, 0, 0, 0, 1, 1, 0, 1, 1. 1, 1, 0, 0 for the not A, just reversing the A column. A implies B. The first two rows here are pretty easy because A is false, so I just go true, true. This is the only false one. If A is true, B is false, we get false. And if they're both true, we get true. And now, not A implies B. So here we have true and true. So the implication is true, 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 true. And now here, we don't really have to think very much because we see not A is false. So we just write ones. Because if that one's false, then it's true. So it's a tautology, and therefore this implication is true. Or yeah, not A does indeed logically imply A implies B. Okay. Any questions about that? Okay. And these things can get more and more complicated. Actually, all the examples I've given you today just involve two different basic statements. You could have 3 statements. You could have 4 or 5. 5 would be a bit evil. You have to write 32 rows. But in theory, you could do that. And like the algorithm for, propagating the ones and zeros would be the same, right? It's just a lot more work. OK. So let me tell you about some other concepts now. So converse and contrapositive. Okay. So kind of as usual, let P and Q be statements. So the converse of the compound statement P implies Q is Q implies P. So it's just backwards. The converse, one difficult thing about this section in the notes or whatever is these words are really, maybe they're not that similar. This one's a lot longer, but they both start with con, right? You're going to need to really keep this straight. What is the converse and what's the contrapositive and how are they different? But this one is the converse. So if I just flip the implication, that's the converse. The contrapositive of P implies Q is, and this is going to seem strange, but not Q implies not P. So let's think about converse and contrapositive. So, are these definitions okay? Okay. So, okay. Let's think about the converse. So I've got P implies Q, or I've got Q implies P. Are these the same? So I guess probably instinctively, you probably think, no, they're not the same. But can anyone give me like an example? Like, maybe like a word, an example in words to say why these are not the same, rather than like a truth table. Okay, if you did a truth table, you can see these are not the same. But yeah, exactly, that's good. So did everyone hear that? So yeah, let's say the statement P is I'm running. Q is I am wearing shoes. Although I think a lot of like ultra marathon, Kenyan runners, like they run with no shoes, but I don't run with no shoes, and I guess you don't either. So it is true that P implies Q. If you're running, you're wearing shoes, but obviously Q. So this is true, but Q implies P is totally false, because all of us are wearing shoes probably. None of us are running, right? So definitely an implication and its converse are not the same thing. They're quite different. What about the contrapositive, though? Does anyone have like a feeling about whether these are the same? Does that sound correct or incorrect in that case? Incorrect. Okay. Well, so if it's true that whenever you're running you wear shoes, if I know I'm not wearing shoes, then you can say that you know that you're not running, because if you were running you would be wearing shoes. The logic kind of feels like it gets a bit confusing, but let's maybe take it to a vote. Raise your hand if you think these are the same. Raise your hand if you think they're not the same. Okay, and then there's a lot of kind of undecided voters here. Okay, so they're the same. Because, yeah, if you think about it, so, if we use the statements, I'm running, I'm wearing shoes. If you're running, then you're wearing shoes. That makes sense. If I know that I'm not wearing shoes, then that does tell me that I'm not running, okay? Because if I were running, I would be wearing shoes. So that kind of tells you that kind of P implies Q implies not Q implies not P in some sense. And the other direction works as well by symmetry. But let's just make sure we know that why these are the same. So we're going to prove, so proposition that P implies Q is logically equivalent to not Q implies not P. Okay, so we do the usual thing, a truth table. Oh, maybe I'll do my nots first. So PQ, and I'll do my not P. I'll do my not Q. I'll do P implies Q. And then not Q implies not P. So we just smash through this like usual. Yeah, I not only recommend you get very accurate at this, but also very fast, because it'll give you a lot longer on tests, right? If you can just slam through a truth table, you'll be in good shape. Anyway, not P, I look at P, I just change the symbols. Not Q, so this goes 0, 1, 0, 1. I should go 1, 0, 1, 0. Now, this one, so for this one, I need to look way back at my original two columns. P is false, so 1, 1. The third one is 0, 1, because the third one is P is true, Q is false. Now I do the same thing, but here. So, but here, remember which one's coming first, right? It's not Q implies not P. So I can say definitely the second row here is a 1, and the second row here is a 1, because that's when not Q is false, right? This one's a 1 because not Q is true and not P is true. This one is false because not P is true. Sorry, not Q is true, not P is false. True can't imply false, so that's a 0. And then lo and behold, if you look at these rows, they're exactly the same. 1, 1, 0, 1. So these are logically equivalent. And logically equivalent means that they're the same. Like they're totally, totally the same. Okay. So that's something to remember. Like the converse of some implication is not necessarily the same as the original implication, but the contrapositive is the same. They're really the same statement. Any question about that? Okay. Let's do another one. Well, okay. Maybe. Okay. No, I'll move on. So, okay. Think about necessary and sufficient conditions. Okay. So this is again like some stuff about implication. Okay. This converse and contrapositive was about implication, and this is going to be also about implication. So, I mean, this is mostly just kind of language and terminology. So it's kind of, yeah, some terminology. So, in the statement, so, well, let's say, given the statement, or compound statement, I mean, really, let's say A implies B. We say that A is sufficient for B, or maybe, so sorry, maybe let me do this another way. Sorry. Let me kind of tie this back to some things we've already said. So sorry for anyone writing notes. Okay, so in words, we've said that this means that A implies B. I think we've also mentioned that this can be written as if A, then B. And I just want to say that there's basically two other ways to say the same thing. Is A is sufficient for B, or B is necessary for A. Okay. So if you ever see something like A is sufficient for B, what it's really saying is that A implies B. I mean, if you sort of like have a good grasp of what these words necessary and sufficient mean, it's kind of maybe clear that why this is all the same, right? So what does it mean A is sufficient for B? It means if I know that A is true, then that's enough information to know that B is true. So that's what it's kind of trying to say, that if A is true, then it's sufficient, it's enough information to know that B is true. And that's the same as A implies B. Whenever A is true, B is true, right? to say B is necessary for A, it means that whenever A is true, it's necessary that B is also true. Like B, to know that A is true, you have to know that B has to be true. So B is kind of necessary for A. Let's look at this in some word problems because I think it becomes a little bit clearer. Let's think about, let's do like a kind of math word problem. So let capital P be a polygon. So what's a polygon, right? It's just a it's just a closed shape, right? Made of straight lines. So what I would say is that, P being a square, well, actually maybe I'll get you guys to fill in the blank, is for P being a rectangle. So necessary or sufficient? Sufficient? Okay. Are we in agreement that this is sufficient? Because it's basically sufficient means, well, what it means is A implies B. So if my statement A is that P is a square, statement B is P is a rectangle, it's pretty clear that A implies B. And so in other words, being a square is sufficient for P being a rectangle, meaning that knowing it's a square is enough information to completely tell me if it's a rectangle. If it's a square, we already know it's a rectangle. So in other words, another way to say the same thing is P being a rectangle is necessary for P being a square. And if you just think of what that sentence means, it's true, right? To be a square, you have to be a rectangle first, So it's necessary to be a rectangle to be a square. Okay. Any questions about this? This is all kind of just giving you more and more terminology. Let me show you a few more logical equivalences. So I'm kind of now going back because I realize we're going to need these logical equivalences later. Yeah, so actually let me kind of, so far the only way I've given you to do anything in this course is truth tables, right? Later though, we're going to have other methods for proving things about logical statements. One of those things is going to involve us basically memorizing a lot of logical equivalences and kind of applying those kind of known logical equivalences to in different situations. So let me give you some, or give you at least one of these logical equivalences. So here's a proposition that P implies Q is logically equivalent to not P or Q. So this is one of these things that we're going to prove it now with a truth table, and you're going to need to remember this later because it's going to, you're going to be given complicated, compound statements, and you're going to have implications, and sometimes it's quite useful to replace the implication with this because this might be easier to work with. And because these are logically equivalent, whenever you see an implication, you can always replace it with this. Okay, so I know these truth tables are getting extremely boring by now, but soon we'll have other tricks, okay? Not P or Q, let's say, and let's do P implies Q. by the way, there's not like necessarily a wrong way to write these columns, so, you know, yeah, don't worry. I mean, in some sense, I want to go from least complicated to most complicated, but yeah. So not P 1 1 0 0. Not P or Q. So maybe I'll get you to help me out. So what should I write in this column? The 4 things. So can you try again? Yeah, probably. Yeah. So 1. Yeah, 1. Yeah, this is the only 0. And then 1. And then we just have P implies Q. We've actually written this one so many times today, at least 2 or 3 times, maybe 4 times. I don't know. You know, P implies Q. If you kind of write your different combinations in this order, it's always going to be 1 1 0 1. And then ta-da, these rows are exactly the same. So these are logically equivalent. So in other words, knowing that P implies Q is the same thing as knowing that either P is false or Q is true, which I think that seems not completely obvious, but it's true. Let's do another one, and then let's do another one, and then maybe I'll kind of remind you the ones we've done, and then we can call it a day. So, okay, so I claim that not P, or maybe let's do 2 more. Let's see. Not P and Q is logically equivalent to not P or not Q. So in other words, you can see there's a kind of like it's kind of like pulling in a minus sign into an equation or something like that, except like, you know, you pull in this negation, put it on the P and on the Q, but then it flips the and to an or, right? I mean, if you just say this in words, it's like kind of clear, right? If P and Q is false, then one of them is false. So this is like either that one's false or that one's false. But let's do it formally with a truth table. So not P 1 1 0 0, not Q 1 0 1 0. P and Q is going to be false everywhere except for the last row when they're both true. A thing to remember, this is and, right? When it points upward, it's and. Not P or not Q. We look at not P and not Q. If there's a 1 in either of them, we make a 1 because this is or. And in the last case, we put a 0. This is the negation of that column. Negation changes everything from 0 to 1 and 1 to 0. And now, ta-da, these are all the same. So it's a tautology. So, or this if and only if that is a tautology, therefore they're logically equivalent. Exactly, yeah. So, and if you're like more comfortable with that, you can do it. So maybe I'll write it here, but this is like another column here. You can write like this if and only if right? And you can do a whole other column for this if you want to, if that's kind of your system. But it is slightly going to be wasting a little bit of time because when you decide whether this is 1 or 0, all you're going to be doing is checking, are these the same? Same. So then you'll write 1, 1, 1, 1. But you could have just said, like, they're all the same, so logically equivalent, right? But so maybe I won't prove this one because we've done quite a lot of these by now. But if I say, or actually maybe I'll ask you. So if I was doing something similar to the last one, what should this be logically equivalent to? Any thoughts? Yep. Oh, so like P, like this. So, well, okay, let's talk about this in words. So, so this one, so this is okay. So actually, technically, in some sense, this can't really be logically equivalent to that because they're kind of negations of each other. This is the negation of that one. Ah, you meant and. So like this, maybe? Yeah, I think all it's missing is then, yeah, it's kind of like this, except you're missing some negations. Yeah, exactly. So we want a not P and not Q. It's kind of like sensible if you kind of think of this in words, right? If either, I take the statement that this happens or that happens, or this is true or that is true. If I negate that, what I mean is that neither of them are true, meaning it's not not P and not Q. Okay, so maybe I won't do the truth table for this one, but I'll just kind of, yeah. So kind of this is a exercise. Well, it's kind of like a something you can do to practice. And actually, it's probably also in the notes. But really, the whole truth table is going to look almost the same as this one. Just, yeah, quite similar. Okay, so which logical equivalences did we learn today? So, and these are going to be important to remember. P if and only if Q is logically equivalent to P implies Q and Q implies P. That's one of them. We probably did more, but let me just, okay, here's one. P implies Q if and only if not P, or sorry, not Q implies not P. That one had a special name, right? Anyone remember the name of this logical equivalence? Yeah, contrapositive, exactly. So which is not the converse. And we had not P or Q if and only if not P, or sorry, I wrote and, I said or, I think. So not P and Q if and only if not P or not Q. And the fourth one was not P or Q is the same as not P and not Q. Okay. We'll be deriving more of these as time goes on. These ones, by the way, they have a name. These are called De Morgan's laws. Or maybe just De Morgan's law. I don't know. Let's say laws. And these will come up later as well. Okay. Yeah, so in theory, you should be able to do the truth table and prove any of these things, but at some point we will be just remembering them and stuff.